Alright, so as part of a community effort, I've decided to start filming some of my sessions here with QRI and my investigations. Some of the science therefore might be wrong, some of it might be right. But I thought I'd show my process of conducting investigations. And today I'm going to show you a daily session on light speed technology. As we get closer to developing light speed technology, it then brings up other questions. And one of those questions is, what is the discrete particle frequency of light? And recently, I'm going to go ahead and bring up this this thing here. Recently, I discovered the frequencies of CN particles. So, and I'm going to tell you in a second what that has to do with light speed, if I can hold this thing properly. Alright. Let's see, I think it goes that way. So, here we have the CP particle, or proton, and it functions at 1,000 hertz, meaning 1,000,000 energy bits per second. And over here we got the complex unit shells, what is commonly known as electron shells. But we will call them in QRI, because we're talking about energy bit processing only, complex unit shells or CN particle shells. So in the K shell of the atom, or the killer shell of the complex unit, as we call it, these CN particles or electrons are functioning at 25,000 hertz, meaning about 25 million energy bits per second. And each shell, each complex unit shell, goes up another 20,000 hertz in order to maintain the orbit around this CP particle in that particular location. And so by the time you get to the Q shell, or question shell as we call it, these CN particles are operating about 145,000 hertz. Whoa, sorry about that. Meaning they're processing about 145 million energy bits per second in order to stay in that question shell. And so it's about 20,000 more each. So 25,000 hertz in the K shell or killer shell, 45,000 hertz in the lying shell or L shell, 65,000 hertz in the mountain or M shell. And I use these names because they appear in signality. In quinary scholarship, we first do these investigations, we determine what is likely the answer, and then we look into signality to find out if this life form, the PLF, has also been documenting these things through standardization. So I was at the mountain shell, which is 65,000 hertz, and you'll see anytime a mountain appears, typically there will be some 65 numerality in there, and I've already seen it quite a bit. Then we have the N shell or next shell, which is functioning at 85,000 hertz. Then it's going to be the O shell or orange shell, as we call it in QRI, in quinary terminology, practical rhetoric. And the O shell is functioning at 105,000 hertz, the orange shell. And next is going to be the points shell, or the P shell, where they function, CN particles function at 125,000 hertz. And then finally, like I said, the Q shell or question shell, which is 145,000 hertz. And it would seem that it's getting kind of hard to hold. The exit frequency for these guys is 60,000 hertz. So if in the killer shell, if the CN particle is no longer functioning at 25,000 hertz, but suddenly jumps up to 85,000 hertz, it's going to leave that complex unit. And likewise for any of these other ones. If the CN particle in the, the question shell starts functioning at 205,000 hertz, it's going to leave that complex unit and head for other territories. So why do I bring this up, and what does this have to do with light speed? Well, it's actually very simple. With DC current, right, the current that's coming from this battery, lithium battery, it's functioning at 0 hertz according to mechanical testing and analysis. And why is that? Well, because they're measuring with electricity the voltage, the alternating current from the voltage. So it's not actually measuring the energy bit processing of these CN particles. And in fact, because it rates it at 0 hertz, we know that there is no ability for measuring the actual discrete CN particles. So this is a huge leap for scientific investigations and a pretty big discovery for humankind. And with light speed, that's going to be another big discovery. But for that, we need to know, I mean, we don't necessarily need to know, but it'd be pure, for the sake of purity, it'd be pure to know the energy bit processing that's occurring with the CO particles and their beams. And so we know that with the electromagnetic spectrum, which I pulled up here, and I'll show you in just a second, we know that, well, I guess I'll show you right now. I'll just go ahead and move it over to see if I can aim this guy. And of course it's not going to do it exactly, because that would be too easy. So we'll just keep on moving this guy so we get a good view here. Alright, so with the electromagnetic spectrum, we know that here's like a microwave here and a radio, sorry, a microwave over here and a radio over here, and a television here, and there's a television right here. We know that these guys, these long radio waves, they get as low as 30 hertz, which means that if that were the case, the CL particles, if they were to take this long, going all the way up there, if you can see the mouse, to let go of those energy bits, they would be traveling kilometers, literally kilometers, in order to drop their energy pieces that they've collected. There's very much no chance that a CL particle is able to hold on that long before dropping its energy pieces. So we know that most likely there's CL particles within this beam gathering, or within this wave here, gathering energy bits and letting them go. But as a group, they're going all the way up here and then coming back down. So, and at 30 hertz, the wavelength is about 10,000 kilometers. From what I've read. So, what we end up seeing then is that most likely the CL particles are getting caught in a wave, like a wave, which might explain the terminology and why I'm going to look into signality with waves to see if I could find the discrete CL particle frequency by using that vocality and seeing if something pops up there. What that means is that the individual CL particles are processing energy bits, and then finally as a group letting them go. So scientifically, I don't know what that means. Does that mean that they're getting caught in a wave, they're processing energy bits, and then, you know, for some reason they're getting caught in this wave and then just going up and down because the energy bits are not as abundant at this point because they've all, at this particular point, processed enough energy bits to then let them go together as a group, and that's what's causing them to go back down this way, or if perhaps they're processing energy bits discretely, and then for some reason when they get to a certain height they no longer can process energy bits as well for some reason, based on the electricity that let them off. The electromagnetic spectrum is caused by electricity passing through a wire, and then it gives off these waves. So the amount of the frequency of electricity flowing through the wire will cause the wavelength here. So the interesting aspect of that is that, does that mean that these individual CL particles are discretely processing energy bits, and then as a group getting affected by gravity too much, and then that's causing them to fall down? Or is it because they're processing energy bits discretely, and then as a group they've run out of energy bits to process at that particular frequency that's comfortable to them, and so they then end up falling down in order to let go of their energy bits, and then as a group start processing again until they, as a group, then have to let them go at the same time, whereas while they're going up this thing, maybe they're collecting some and letting some go, collecting some and letting some go individually, but then as a group for some reason they decide to do so at this point. I don't know. This is something that I'm going to be working on at QRI and trying to determine. And it's also possible that as the frequencies get increased, it goes ultraviolet, X-rays, and the gamma rays here, maybe as they increase in speed, or in frequency speed, it gets closer to the actual discrete energy pieces that are processing energy bits. So, and we would need to determine at what point that occurs, and whether the wavelength goes faster, the wave ever goes faster than the energy processing of the CL particles. So there's a lot of things to answer there, and I'm going to go ahead and zoom out here. So why is that important? Well, in order to, have a, gotta move this back over here. In order to have a detonated and a detonating CL beam, we need to know the frequency of these energy bit processing CL particles, and we need to know if they're letting them go as a group, at what frequency it would be necessary to create light speed. It could be possible that the first opportunity at light speed would be when the wavelength matches the energy bit processing of the discrete CL particles. So that could be one of the factors as to why we're not able to create light speed with certain beams or at certain frequencies. So this is what I'm working on with QRI, and it's December 3rd, and I guess I'll record another session. I'm going to also record some sessions of me doing the signality and documenting it, so that people get to see that process, and maybe some other things. But I just wanted to start documenting these things because other people are going to be quinary scholars someday when I open up my institute for public use, and these are the questions that they're going to have, and they're going to probably wonder, how do I go about investigating things? What kind of questions should I be asking? And these sessions will most likely help to demonstrate how I go through these things and how I've been so successful at finding specific data over the last 8 years. So I'm going to go ahead and end it there, and I'll see you guys another time.